Hi, welcome to Law 6, Term 1, Chapter 4. Okay, Chapter 4 will be about work done, energy, and power. Okay, so it's a three basic concept. So the first one, what we are looking at is 4.1, which is the work. So you have to define the work now at your level. It's not the same as you define the work done in Form 4. So our work done is defined to be the dot product of the force applied and the displacement of the object. Alright, so that is more mathematically rather than analytically. So our formula for work done, W is equal to F dot S. Alright, so F is a vector quantity, S displacement is a vector quantity, but dot product give us a scalar quantity. Okay, that is a scalar work done. So you are based on this definition. Okay, so that is the first part of our chapter number 4. Now look at this definition, F dot S. We know that since A dot B is equal to the magnitude of A multiplied by magnitude of B and then multiplied by cosine theta, where theta is the angle between the vector F and vector S. So now normally we just drop out the modular sign when we drop this vector sign. So your A dot B will become just simply AB cos theta. Okay, AB cos theta. Now that means our W is equal to Fs cosine theta. So that is our magnitude for the work done. No direction anyway. So physically, if we use a diagram to show what is happening, let's say you have an object. Okay, you have an object with a mass m on a surface. Okay, on a surface, if you apply a force F onto the object and then the object move a displacement S, and if the angle between them is theta, only these two vectors, so the work done on the object is equal to F dot S or Fs cosine theta. Your previous definition in Form 4 actually used this concept. We know that our F can be split into two components. Okay, one is this F parallel to the S, another one of course is this one. Okay, this component here. So I will draw that component in green color. That component is vertical. This is the F perpendicular to the surface. So when I say parallel, is parallel to the surface or the displacement. Perpendicular is perpendicular to the displacement or the surface. Now, this component F parallel is actually equal to F cosine theta. So your work done last time is said to be force multiplied by displacement, so it is this component of the force. So this one multiplied by this is actually give you this. But that is not an entirely correct definition. The correct definition is a dot product definition. Okay, so since you haven't learned dot product in Form 4, so that's why they use that lower level definition. So then now you already learned your dot product in chapter 1 or 2 in your term 1, so you are supposed to use this type of things already. Alright, now how about the green component? This green component is only important if your surface is rough, because we know that if the object M is placed on a rough surface and when you pull it, it's going to experience friction. So that friction is because of the normal reaction. But since there is a component of F perpendicular to the surface, so our normal reaction will be slightly smaller if you pull object like that. If you push from the other direction, you are actually make the object seems like sinking down to the surface, so you are creating larger normal reaction, and in that condition your friction will be increased. So that's why it's more advisable to pull object rather than pushing them, because pushing them is creating more friction, pulling them up is actually reducing the friction. All right, so you only use this component when there is a friction. We will look at that one later. All right, so example on this type of things here is like this one. Okay, we look at example 1. So let's assume an object, okay, is placed on a surface. Okay, this object is placed on the surface, and then it has a mass m, okay, which is 2.0 kilogram, and then the object is applied a force F of, let's say, 20 Newton, and it is displaced by an amount of 15 meter. And extra information is the angle here is 40 degree. Okay, it is 40 degree. So the question is calculate. Okay, calculate the work done. Okay, sorry, I put it into ABC better. Number A, calculate work done on the block or the object if no friction is existing. Okay, if no friction is existing, that means the surface is smooth, or can just simply say if the surface is smooth. Number B, calculate the work done on the block if, okay, work done on the block if the kinetic frictions coefficient mu k is 0.34. All right, so that is our question. So here you are given G is equal to 9.81 meter per second per second. You need that because later you're going to use that one to find the weight when come to the second part of the question. Okay, our first one, A, this is our solution. So A, work done on the block if no friction. So that means the block experienced no friction at all because the surface is assumed to be smooth. So that means in our drawing, we only have this force F and this displacement S, and the theta is 40 degree. So we can calculate our work done by using this formula. So since this is a work done by the force only, so there's no need to put a subscript here, but it's good to make a habit. Work done by what? Work done by the external force F is equal to the force dot S. Okay, because later in question number 2 we are going to have friction, so you're going to need another symbol for the work done. So this one will give us Fs cosine theta, and this theta is 40 degree. So our first one, this one is 20 Newton, displacement is 15, and cosine 40 degree. Okay, so calculator show us that 20 times 15 times cosine 40 is equal to 230 joule. Okay, 230 joule, or the unit of work done is also equivalent to Newton meter. Okay, so that's the first one. Is actually quite easy. Now the second one is a little bit trickier. Now the diagram, okay, is like this. And then in this case, we're going to have friction. But the force is still the same. Okay, the force and the displacement is the same. Displacement no changes. The force is still the 20 Newton F, and the angle is still 40. And then something extra here is the friction. Okay, this friction I will give it small f. Okay, small f. And then we know that from your previous chapter, okay, friction is actually equal to mu r. Okay, mu r is normally mu n. Okay, mu n. So it's preferably to use mu n. But in this case, why we use mu n? Because we know that the normal reaction must be perpendicular. Okay, but sometimes why we use r is because we're going to have inclined plane. So when it comes to inclined plane, most of the time we use a mu r. Okay, mu r. But this mu here is when an object is moving, so it is a mu k, kinetic friction. Now, other than that, we need to know something. Refer to this diagram. If this f perpendicular is only important when there is a friction. So in this case, we're going to split this thing into two components, one horizontal and one vertical. So this one is we only look at the vertical part, okay, because it will only influence our friction. So this is a f perpendicular, and this one here is the f parallel. Okay, f parallel. So if you look at the diagram, we know that the object has weight. Okay, it has weight. Weight is an action. Okay, weight is an action. So this is a W equal to mg. That's why we need the g here. And then because of that, it will have also reaction, normal reaction. But our friction, okay, our friction here is based on the effect of the total normal reaction. Okay, total normal reaction, this one, okay, plus this one. So that means our object here, okay, you see, it experience zero vertical forces, okay, zero vertical net force. So the net force here, if we assume going up is positive, down is negative, so that means our n plus f perpendicular is minusing your mg must equal to 0. Okay, down is negative. So this is what we need. This is going to be inserted into this one. So our n is equal to mg minus f perpendicular. So now it makes sense. When you carry something, when you pull something at an angle above the horizontal line, you are creating a component actually to reduce your n. Okay, you are reducing the n. So that's why your friction is going to be smaller if you pull object like that rather than pulling downwards. Okay, so first we need to calculate the n. Okay, so our n is equal to the mass is 9.81, and then minus this one. Okay, we have to minus this one, that is 20. Okay, 20 sine 40. Okay, 20 sine 40. So that is our value. So I have 2 times 9.81 and then minus 20 sine 40. Okay, so we have 6.76 Newton. Okay, 6.76 Newton. That is our normal reaction which you're going to use for this F. Alright, so we calculate our F. Okay, is equal to mu R, and your mu is 0.34 and your R is 6.76, so that will give us 0.34 times 6.76, that will be 2.30 Newton. Okay, 2.30 Newton. Okay, that is our F. But remember, F is pointing to the left hand side. So now we calculate work done, okay, on the object. Now your work done on the object, you have two. Work done on the block is equal to the work done by the force F, and also plus the work done by the friction. Okay, now the work done by the force F is already calculated, which is equal to 230. Okay, we'll leave this one alone first. But your work done by friction now is what? We use the same definition. Work done by friction is friction dot displacement. Okay, so friction dot displacement, you have Fs cosine 180 degree, because your friction is pointing to the left when your object is moving to the right. So displacement vector is to the right, this one to the left, the angle between them is 180, and this one gives you -1, so it ends up like this, minus Fs. Okay, so we can put in the value now and calculate what we have. 230 minus this one is 2.30 multiplied by 15. So our total work done on the object is this, 2.3 times 15. Alright, and then we minus 230. With this answer is 195.5 joule. Okay, so that is the work done. So you see that the work done on an object when there are friction is going to be less than the one when there is no friction. So what does this mean? This means that when you do work on some object, it will start to increase in its velocity. Thus, it will gain kinetic energy. But since part of the energy is used to go against the friction, so the motion with friction compared to the motion with no friction is this. Energy work done on the object will be the same. Okay, total work done will be the same. But for the one with friction, part is converted to heat due to the friction. So that means the final effect is, the final condition is the object will gain less kinetic energy compared to this. Work done normally convert to something else. Okay, work done is normally convert to like kinetic energy, potential energy, and some other energy. But in this case, you only look at three type energy: the kinetic energy, gravitational potential energy, and spring potential energy. Okay, so that is an example on work done. Okay, but this one is only on a flat surface. Okay, flat surface. And then we go to the next one, which is the how do we get the work done, okay, when you have a force displacement graph. Okay, so that one will be still under force displacement graph. Okay, this is our page number 1. Now page 2. Okay, graph of force against displacement. Okay, graph of force against displacement. Okay, now for example, you have a graph like that, and let's say the force is changing relative to S based on this function. Okay, just for example. Alright, so if you want to calculate the work done on this, you are going to need to find the area below the graph. So the area is equal to the work done by the force. So work done is equal to the area of S versus S. So that means your work done is the integration of the function f at S. Okay, so one more thing you need is you need to limit it is from 0 up to this one S. Okay, whatever value you have. But the problem is it's not that easy to get the force function according to S unless it is given to you. Then you can use this method. But normally the question in your exam, okay, in your final exam, normally they will give you graph with the shape that you know how to calculate. For example, shape that is like that. Okay, the shape that is like this. So obviously this is a trapezium. So for trapezium, if you want to calculate the area below the graph, you need a few things here. Okay, you need a few things. For example, the height, which is this one, okay, the height of the trapezium, or the distance between two parallel sides. Let's assume this is h, okay, and then you need also this value, okay, this value where they started to change the gradient. I call this one A, and this one is B, okay, and then this one is C. Now we know that the work done is equal to the area of trapezium. Okay, so that means our area is half, okay, half of the height multiplied by the summation of these two sides. The side here, okay, this one here is B minus A, okay, B minus A, and then this side here, the total length is C, from 0 to C. So that is the way we calculate the work done. If you are given graph like that, then you have to do some sort of integration, okay, but you don't have to worry about this one. You just need to know it is like that. But normally question is like this, okay, it can be trapezium, it can be combination of trapezium and a square and so on, it can be only one triangle and so on. All right, so that is a graph of F against S, and how do we get the work done? By using this method. All right, now we have some other things for the work done also, okay, but that one we'll leave it after we look at energy, okay, our energy. So work is related to energy in something that we call the work energy theorem. We need to look at energy before we can look at the work, the theorem. So the next one, 4.2, okay, our 4.2 is energy, okay, energy. But how many type of energy are we going to look at? Well, the first one is the kinetic energy, okay, and then number 2 is the gravitational potential energy. And the third one is spring potential energy, or sometimes you can also use elastic potential energy. So these are the 3 types of energy that you must know. All right, so all these are actually considered as mechanical energy, especially these two. Kinetic energy, I will use a symbol EK. Gravitational potential energy, EP, and spring potential energy is ES. Okay, so that there's no confusion in the symbol use. Sometimes books will use big capital letter K for kinetic energy, big capital letter U for potential energy, and this one they just simply use S. Okay, they use S or maybe just some other symbol. So these two are important, okay, kinetic and gravitational potential. So our gravitational potential energy here, okay, combined with kinetic is sometimes called the mechanical energy. So we look at them one by one first. Okay, kinetic energy, we don't derive the formula, we look at the energy formula straight away. For kinetic energy, you need to have object with a mass and then moving with a velocity v. This is a mass m. So the kinetic energy formula is actually half m, the magnitude of the velocity square. And we know that the magnitude of the velocity is actually equal to the speed. So you cannot square a vector, but you can square a speed. So that is our formula for kinetic energy. Okay, so that is a first formula for kinetic energy. And of course, energy have a unit of Newton meter or joule. Now, second one is the gravitational potential energy. And this one is EP, okay, EP, this one is EK. Now, gravitational potential energy has something to do with the height of an object and also the gravitational field. This height of object normally refer to the center of mass, okay. So let's assume the height of the center of mass of this object with a mass m is h, and the surrounding gravitational field is g. So the energy, the gravitational potential energy, okay, for this object at such a height is mgh. But you can only use this formula when the object is near us. Only can be used when near us surface. Because why? The reason is when you go further and further from the surface of the earth, our G value started to change. So then you have to use some other formula. That one we'll look at when we come to Newton's universal gravitational law. That one is a more complete equation used to deal with the G here. Alright. Now at the moment, as long as your object is near the earth, okay, then our G is quite constant. So what is the G? 9.81. To calculate energy, we don't have to use a symbol, the negative sign anymore. That negative sign is only in free fall and projectile motion. Okay. Now next one, our C is the spring potential energy. Which is ES, the spring potential energy. It has something to do with like when you pull a spring. Okay, when you pull a spring. For example, a spring with original length like this. Then you pull the spring to a new length like that. Now there is a changes in displacement of the spring. So this is the X. X, if this is the original length and this is the new length, so your X will become new length multiplied by original length. Right? New length multiplied by original length. And of course, you need to apply a force to make that changes. Okay, so our formula to calculate the spring potential energy is half kx or equal to half kx squared or equal to half k, this one is L minus L naught square. Okay, half kx square or equal to half k L minus L naught square. The k here is a spring constant. It tells us how stiff is the spring. If the k is small, that means the spring is very easy to be pulled, and if the k is huge, it's a very hard spring, very stiff spring. Okay, so that is your third formula for this part for energy here. All right, for energy here. So these are the three basic formula that you must know and how to apply them. And especially these two, especially this one, is a very relative value. For example, when you move an object from the ground up 10 meters, so your energy will be mgh, with a h equal to 10. But let's say you are moving an object which is already at 10 meters. You move it up another 10 meters, so now the changes in the height is still 10. So your change in energy is the same like before, except the final one related to the ground is double.